Yup. So the project. Well, I'm not really good at kind of introductions, but since the beginning of time, Circuit Breakers presents from the beginning of the Big Bang to the Cretaceous to now, we have been facing the same thing. We have been facing extinction. We've been facing murders. We've been facing craters. So our team created a project. We got together on a mission to protect the Earth with Dhanasri Prabhu, Radha Chauhan, Huang, Katherine Korb, Felicity Wang, and the instructor behind it all, Ethan. Yeah.
Thank you so much for that amazing introduction, Radha. Okay, so I'm going to start us off by talking about the timeline of the project. So week 1, we learned Python basics and packages such as NumPy and Pandas. Then we researched and found a data set in Kaggle, which then we removed and cleaned any unnecessary data from the data set. Then we used Plotly to create graphs and charts like scatter plots, pie charts, and more. Week 2, we finished cleaning the data set. Then we researched for some supervised classification models for the project. We trained and fitted the classification models and picked the highest performing models for the final project. Then we learned about random oversampling and fixed the imbalance problem that I will tell you guys more further on. Week 3, we learned about HTML and CSS and applied our knowledge to create this very website.
So let me start off by saying this is my favorite section of our website. It's our actual product. Now, us being from our data science group, we didn't have to have any sort of backend to our website. All of our quote unquote backend and research was pretty much done throughout our notebooks and the time itself, learning for the past couple of weeks. And then this is just supposed to be like a presentation of all of our data. But we had a lot of extra free time on our hands. So especially Radha and Dhanasri, they took time after class, like a long time after class, and helped get the rest of our website ready so that we could enter this in. So big thanks to them. Essentially what this portion does is it displays our data and it predicts whether or not a hypothetical asteroid would be hazardous or not hazardous to Earth, depending on its velocity and magnitude. So that one was hazardous. And then if we put in a non-hazardous model, it'll show up as non-hazardous. So basically, to review everything that was kind of said in the beginning with our timeline up until here, our project was totally inspired by space. We had a couple other options for data sets that we had gone into previously, but this just felt right. After learning our Python, we looked through 4 different machine learning models, and now using oversampling to improve our accuracy of the data set that we had retrieved, we created HADS.
Okay, so after cleaning up our data set, we decided we had to make some graphs. So below are some interactive graphs that we'd like to share with you guys.
So first up are our correlation matrices. It's essentially a table that shows relationships between different variables within our data. The matrices in general are used to summarize data and for professional diagnostic tools for advanced analysis of any data. These can be applied to anything, and they are used basically worldwide by data scientists to help prove theories, and et cetera, et cetera. Negative correlation is in the cooler color for this chart, and that means that the 2 variables have little to no relevancy to each other, or they don't interact very much. Or the warm colors in this chart shows that the variables do have a direct effect, where you can see relative velocity and relative velocity have a 1-to-1 correlation because they are the exact same thing. But mist distance and relative velocity, you can see their connections because they are in a warmer color.
Okay, I will be talking about the imbalance problem. So the pie chart below shows the percentages of non-hazardous and hazardous asteroids that were in our data set. A problem that we encountered when building our models was that there were more data entries for non-hazardous asteroids than hazardous ones, causing an imbalance. So to be exact, there were 81,996 entries of non-hazardous asteroids, while there were only 8,838 for hazardous asteroids. And this imbalance caused our accuracy metrics to lower significantly to the 50 to 60%. So we decided to fix it by using the random oversampling method, which adds more copies to the minority class. In our case, that would be the hazardous asteroids. And as you can see, after doing random oversampling, the number of non-hazardous and hazardous entries are the exact same, 50-50. Okay, moving on, we have our box plots. So this first box plot shows us the relative velocity, comparison of relative velocity with the non-hazardous and hazardous asteroids. This one particularly shows us that the hazardous asteroids have a higher min, max, and median than the non-hazardous asteroids, which means it does have a contribution. Relative velocity does have a contribution to whether or not it is hazardous or not. Same thing here with absolute magnitude, but except the hazardous asteroids have a lower max, min, and median than non-hazardous asteroids. And then lastly, we have the mist distance. As you can see that the box plot shows us that the hazardous asteroids and non-hazardous asteroids have almost an equal median, min, and max when it comes to mist distance, which means it doesn't contribute to whether or not an asteroid is dangerous.
All right, so the two scatter plots that you're going to be seeing right here is relative velocity versus the diameter. The top being relative velocity versus the minimum diameter, and the one below that being the same thing except versus the maximum diameter. As you can see, the only difference between these two graphs would be the y range, mainly because it's only diameters that are different and velocity is the same. Both the hazardous in the red and the non-hazardous in the blue are in the same space and don't really change. Because of the minimal differences between these two graphs and the non-hazardous and the hazardous data, we decided to take these off from our input variables for they show relatively no correlation to whether that asteroid was hazardous or not. So we chose to not include them and for our product. This was one of our more interesting graphs. This one is relative velocity versus the absolute magnitude. So as you can see here, the hazardous in the red, all are limited to only about 22.6 degrees for the absolute magnitude and will not increase and go over there. And for the blue points with the non-hazardous, it doesn't exceed about 32 degrees. And they all stay relatively within the 150,000 kilometers per second for the relative velocity. And this data was actually really important because of the severe differences between the two non-hazardous and the hazardous. We found these two to be one of our most important variables, so we use that mainly for our product.
Our team initially tested 9 models, and 4 of them, the ones below, were the most promising ones. All 4 of them had accuracy metrics in the high 90s, and the confusion matrices had a majority of true positives and true negatives. We also tested the gradient boosting classifier Bernoulli method model, Gaussian models, support vector machines, and logistic regression, but their metrics were not as up to the standards. So the first model we tested was decision trees, and that's actually the one we ended up using. Decision trees are like flowchart tree-like structures, where a system uses a series of questions to assign a classification. We ended up using this model for our final project because of its high accuracy, especially in the really high 90s. And then our second model in the top 4 was K-nearest neighbors. K-nearest neighbors is a non-parametric method used for classification. It works by selecting the specified number of neighbors closest to the query and then votes for the most frequent label based on the neighbors. For these, they all had high accuracy metrics except for precision, which was in the 80s.
All right. So the random forest tree classifier kind of works by having like a bunch of decision trees kind of running. And then with the predictions that it makes, it chooses one by means of voting. And this one was actually one of our highest scoring models, and that it was like second place to decision trees with an accuracy, recall, and F1 score all in the 90s and only a precision score in like the 80s.
The second one.
Oh, sorry. The XGBoost is a similar model, but kind of works by having a bunch of weak tree models that it kind of merges together to create a stronger model. And this one was also a pretty strong one, not one of our best, but one of our better models with accuracy, recall, F1 all in the 90s, and a precision score in the 80s at 83.51. And I believe actually the one that I was talking about before, the random tree forest classifier, had all 90s.
Okay. I will be talking about the confusion matrices of the four models above. So confusion matrices are one of the many methods we use to confirm whether or not a model is sufficient. The goal is to have a high number in the true positive or the top left box and true negative in the bottom right box, because these values are correctly predicted by the machine learning models. The other two boxes contain the number of incorrect predictions. And as you can see, all four of these matrices have pretty low numbers in the top right and bottom left boxes.
All right, before I leave you off with final words, I'd like to give a little shout out to Claire for she's not here with us today, and to thank a certain instructor that brought us along the way, just like help us out. So thank you, Mr. Ethan, teacher guy.
Thank you.
Thank you.
Thanks.
You really led us to get to where we are, and thank you for these past 3 weeks. It was a delight. All right, so there's this thing I've been doing with the past data science groups that your batch, unfortunately, not all of you might know. I am here to leave you off with a few words that I want you guys to remember. Asteroids are the vermin of the skies. Walter Blake. Thank you for listening to our presentation. Thank you.